A fixed-pitch propeller receives its relative airflow from a direction governed by the aircraft's true airspeed in the direction of flight and its own RPM in the plane of rotation. The operating angle of attack will be the angle between the relative airflow and the chord line of the propeller blade. This chord line will be set at an angle to the plane of rotation, that is, the blade angle or the propeller pitch angle. This animation shows that an increase in RPM will increase the angle of attack, whereas an increase in true airspeed will reduce it. At high forward speed with low RPM, for instance in a power-off dive, it's possible to reduce the angle of attack to 0, while at a low true airspeed with a high RPM, for instance in a climb, it's possible to stall the propeller blade. Both extremes are obviously inefficient and therefore undesirable. The conclusion that must be drawn is that for a given fixed pitch, a propeller will only work efficiently at one combination of true airspeed and RPM. All these considerations illustrate why more advanced aircraft have engines which are fitted with variable pitch propellers. There are several different types of variable pitch propellers. Here are some which the private pilot may come across. Adjustable pitch propellers are propellers which can have their pitch adjusted on the ground by mechanically resetting the blades in the hub. In flight, they act as fixed pitch propellers. Two-pitch propellers are propellers which have a fine and coarse pitch setting that can be selected in flight. Fine pitch can be selected for takeoff, climb and landing, and coarse pitch for cruise. Two-pitch propellers will usually also have a feathered position. Modern aircraft have propellers which are controlled automatically to vary their pitch, the blade angle, so as to maintain a selected RPM. A constant speed variable pitch propeller permits high efficiency to be obtained over a wider range of true airspeeds, giving improved takeoff and climb performance and cruising fuel consumption. This diagram illustrates a typical set of engine and propeller controls for a small piston engine aircraft with a variable pitch propeller. Throttle, propeller, and mixture are shown in the takeoff, all-forward position. For a given throttle setting, pulling back on the propeller control will decrease RPM by coarsening the pitch of the blade. Conversely, pushing forward on the propeller control will increase RPM by fining off the pitch of the blade. Once RPM has been set, it will be maintained within the operating range of the throttle lever. This shows conditions during the early stages of takeoff roll. The RPM is set to maximum and the true airspeed is low. The angle of attack is optimum and maximum available efficiency is obtained. As the aircraft continues to accelerate, the true airspeed will increase, which decreases the angle of attack on the blades. Less thrust will be generated and less propeller torque. This gives less resistance for the engine to overcome, and RPM would tend to increase. The constant speed unit, or CSU, senses the RPM increase and increases pitch to maintain the blade angle of attack constant. This diagram shows the conditions at high forward airspeed in level flight. As the true airspeed increases, the constant speed unit continually increases the blade angle, or coarsens the pitch, to maintain a constant blade angle of attack. If a loss of engine torque occurs, the throttle is closed or the engine fails, the propeller will fine off in an attempt to maintain the set RPM. The relative airflow will impinge on the front surface of the blade and generate drag and negative propeller torque. The propeller will now drive the engine. The drag generated by a windmilling propeller is very high. A single-engine airplane fitted with a constant-speed propeller will not have a feathering capability as such. However, following engine failure, drag can be reduced to a minimum by moving the propeller pitch control to the fully course position, as shown here. In a steady glide with no shaft power from the engine, the throttle closed, if the propeller pitch is increased by pulling back the prop lever, the aircraft lift-drag ratio will increase. This will decrease the rate of descent. The RPM would decrease because of the reduction in negative propeller torque.